welcome to today's presentation, which is on why do metal bearings fail? And you might wonder why TriStar, who doesn't make metal bearings or sell metal bearings for that fact, why are we interested in why metal bearings fail? Well, what we want to talk to you about is what you can do in cases where your application may see more frequent metal failures than you would like to see. We have a lot of different options in terms of non-rolling element materials. And so what we wanted to do was present some of the reasons that metal bearings do fail and how non-metal bearings can counter that. So let's talk a little bit about where you see failures. If any of you have taken bearings out of an application or had somebody bring one in from out in the plant or wherever, a lot of this may look familiar. And so what we want to do is describe the many different types of failures that metal bearings experience and address those along the way as to what our solutions could be. So if you look at the parts that are involved in a rolling element, there's a lot. I mean, there's inner and outer races, there's cages, retainers, seals, the balls, and this can be any number of different configurations. But the key point is you have many different moving elements here, and it always has to have lubrication. There have been some attempts over the years to come up with filler materials that are made out of lubricating materials like graphite and so forth that actually act as the ball retainers as well. Not too much success with that, but you know, ball bearings have been around for a long time, and the technology has gotten better over the years, new metals, new lubrications and things like that. But at the end of the day, there's still a number of different things that can go wrong. So if you look at the different configurations, you know, as you're aware, if you're using any kind of rolling elements, there's a number of different ways you can get these: single roll ball, double roll ball, tapered rollers, cylindrical rollers, thrust washers, thrust bearings, all, again, multiple components, all requiring lubrication. And that's what we want to get around in this conversation, is how do you solve bearing problems with non-rolling elements and no lubrication. So if you look at the way lubrication works with a rolling element, you basically have to have some form of lubrication, whether it's a light oil or a grease, in order to produce that film or that elastic content or contact between the ball and the races. If you lose that lubrication for whatever reason, or if that lubrication becomes contaminated for whatever reason, that begins this process of bearing failure. One point I want to make here, though, is that you notice that because this bearing is moving, it's constantly generating this film. So as you have the race and the ball in contact, and there's this continuing motion, it's continuously bringing new oil around, and that's a perfect condition. The problem is, too many people try and use a rolling element bearing in oscillating applications or even linear applications. That is not conducive to this constant feed of a lubricating film. And so we want to talk a little bit more about that when it comes to plain bearings, because plain bearings, self-lubricating plain bearings, we don't have that problem, and that's why more and more people recognize that this is a problem with an oscillating rolling element. You can't get that film, and as a result, you will get some lubrication starvation and then some of the other problems that we'll talk about here as we move forward. Timken, a number of years ago, actually hired MIT, of all people, to do a study, and they contacted several hundred maintenance facilities, MRO technicians, and asked them, what is the number one problem that you see in your plant in terms of bearing failures? And the answers were pretty typical of what Timken and everybody else in the bearing business already knows, and that is that 50% of the failures that are experienced in a manufacturing facility, either as an MRO point or even in OEM applications, 50% of them are related to lubrication. And those are typically either the incorrect lubrication is being used, Viscosity is wrong for the application. Inadequate maintenance. If it's a bearing system that's set up with a Zerk, and you don't go in there and purge the contaminated grease or replace it, or it just goes away, bad maintenance. Over lubrication. 70% of the maintenance people that they talked to said that they felt over lubrication in a lot of cases was their problem. I've been to a lot of plants in my time, and the conversation always goes this way. Well, we just pump it full of grease until it starts oozing out. That's not necessarily the right thing to do. I mean, it's okay if you're trying to get rid of contamination, but that's not necessarily the solution. And I think a lot of the maintenance people realize that. And then the other big cause was contamination as a result of seal failures or the lack of seals. You can buy rolling elements with or without seals, and there's different types of seals. There's double seals. And sometimes, no matter what you do, those seals will fail, you contamination, and that's the beginning of the end. So as we move forward, these are some of the things that can happen as a result of lubrication problems. Brunelling. And we'll talk more about what that means. Lube failures can move to micro-adhesion between the balls and races. And this little graph there, this picture down here, kind of gives you an idea microscopically of what happens. When you have two metal surfaces rubbing against each other, you're going to generate a certain amount of micro-adhesion, which generates little small particulate that becomes a wear component. And so the lack of lubrication obviously is going to generate more of this sloughing off of metal, and that leads to wear, that leads to the abrasive wear. Lubrication also causes overheating. When you overheat a ball bearing, especially if it's a high-speed ball bearing, you can get expansion, thermal expansion of the steel, and it leads to seizing. And then if the contamination gets in to the lubricant, then that becomes a lapping compound. It basically, you might as well just put some kind of metal oxide in there or something like that and just start abrading away, because that's exactly what this contaminated lubrication will become. So let's take a look at some of the key issues with ball bearing or metal bearing failures. Spalling failure, premature fatigue, and tight fits. These are all issues that are a result of excessive loading. Tight fits, brunelling, and preloading can bring about failure. Now, tight fits is basically just really has to do with your hardware and is it correct? Do you have too much press fit? Is it squeezing in from the outer race onto the ball to the inner race, even down to the shaft? You wouldn't think the steel bearings can have that much compressibility, but they really do in certain conditions. Preloading is another thing, and there's different types of preloading. You can preload mechanically, you can preload by the way you're installing it, and sometimes if that's out of balance, you can get this excessive loading situation. So, it's one of those things that you don't think about, because you look in the book and it says, here's what your tolerances need to be on your hardware. The bearing is made to certain tolerances. It should just be press fit and away you go. A lot of things can happen during that press fit, whether it be this improper preload, or it could be something as simple as a slight offset and you get a misalignment on the shaft, and it just eventually leads to the type of failures you hear with the spalling. That all comes as a problem from too tight of a fit. So, for TriStar, our solution is situations like this is to have the right material to handle that excessive load and do it without having to worry about lubrication. So we can really deal with a lot of loads in excess of even metal bearings in some cases. And I'll tell you right here, we can't replace all metal bearings. It's just silly to think that. Plain bearings are not designed to replace across-the-board rolling elements. But there are certain conditions, like I mentioned before, oscillating and linear are two areas. But things like excessive loading, even beyond what metal bearings are capable of doing, we have some of the capacities to do that with our materials. Corrosion, big problem. Corrosion comes from a lot of different avenues. It can be chemical corrosion, it can be moisture corrosion, it can be just that the lubricant is not doing a good job of properly coating the metals. You can get fretting corrosion, which is a totally different animal. That's more of a mechanical corrosion. And over time, you develop this very deep-seated rust, and that rust itself becomes now a contaminant. And so it's just this kind of this ongoing cascade of failure modes that will eventually take out the bearing. Here's an example of what deep-seated rust looks like. And again, depending on the application, you will get a certain amount of corrosion. Even moisture, if you've got bearings in an application that are outdoors, that's outdoors, you're going to get some amount of corrosion in those bearings, even with stainless steel bearings sometimes. So what you have to really depend on is for the metal to be doing what it's supposed to do properly, the lubrication being doing what it's supposed to do properly. But when you start this process of deep-seated rust, it will start to flake, it will start to corrode the steel deeper and deeper. And eventually you will actually have catastrophic failure, or basically a wear failure that takes place. A lot of this can take place, obviously, in water applications. You get corrosion, galvanic corrosion, and then in salt water, there's a whole different animal when it comes to salt water, and TriStar has a number of different options to offer in terms of bearings in salt water. Fretting corrosion, this can occur basically as a result of movement. There's a lot of particulate movement that's taking place in the bearing, even in a perfect condition. Oxidation can take place, and as that all takes place, it begins to get deeper and deeper into the metals. And over time, you'll start to get these little patterns, these little wear patterns in there that are really fretting from that inconsistent loading, that inconsistent generation of contaminants, oxidative contaminants. So this is something that's internal to the bearing, and obviously, again, it has to do a lot with what's going on externally and what's going on internally with lubrication. But this is a commonly known failure mode for bearings. Brunelling, true and false brunelling. It's two very different types of brunelling that take place, and the best way to describe brunelling is pitting. And you can see from these pictures there are some very definite differences between true and false. True brunelling is something that you would normally see if there's a lot of impact or overload taking place in the bearing. And it really is just this constant pounding away between the balls and the races. And you can hear that sometimes, even in an automotive bearing, you can sometimes hear this clicking noise. And it's not uncommon to hear in a wheel bearing. But you hear this little clicking noise. And sometimes that is this brunelling process that's taking place, even in a lubricated condition. If the lube gets used up pretty well or gets old, you can start to generate this brunelling. False brunelling is a little bit different animal, same type of result. You get these little holes in the races, and that basically happens when you're now getting a more consistent rotating metal-to-metal contact. And this also can occur as a clicking noise, just because of the indentations that take place. So brunelling is also a very common cause of bearing failures. If nothing else, it's a nuisance. If you can hear it, it's a nuisance. Here's a better definition of brunelling. I kind of explained all this, but sometimes with true brunelling, the exact definition is you've exceeded the elastic limit of the steel, in essence. And again, that's hard to understand sometimes because, Sometimes the races are hardened, the balls are hardened. A lot of people now are using ceramic races or ceramic balls to kind of get past this. But ceramics is a whole different animal and brings up a whole lot of different problems. But, you know, again, brunelling is a common problem, and with polymer self-lubricating composites and non-metallics, we are able to deal with a lot of these issues that can basically resist these types of compression or elastic conditions that you would see with metal on metal. So contamination, again, contamination, again, comes from a lot of different forms. This is probably the thing that's most visible in a bearing failure. And again, the contamination can come from all different types of things. It usually is from grease that's been improperly maintained. As I mentioned earlier, it's a situation where you get contamination there, it becomes a lapping compound. You get the rust, you get all kinds of other things going on. And so eventually it just leads to a complete failure of the bearing. And it really points back to the original discussion on why bearings fail. And contamination and lubrication are the two big ones. And lubrication obviously is directly relative to contamination. If the bearing is properly maintained and you keep the contamination out, either through proper seals, proper lubrication, then these types of things won't occur. But they do, and so that's again where self-lubricating polymer bearings offer some different solutions, because we don't worry about corrosion. Our materials are non-corroding, and we don't have to worry about lubrication either. So a lot of the things that cause bearings to fail are things that we can solve with polymer bearings. Some other bearing failure terminology: fretting, overheating, which again can be caused from improper fits, just the wrong lubrication for the ambient environment that it's working in, lack of lubrication, wrong type of lubrication, reverse loading, misalignment. Of course, misalignment is if you either press fit the bearing in slightly off-centered. You can get some misalignment between the shaft and inner race, and then the inner race to the balls and the balls to the outer race, and it just kind of compounds all the way through the bearing. And spalling from fatigue failure, and then again, finally, improper fits. Solutions, again, all of these can be solved by using the correct polymer and composite technology. Now, I thought I'd mention, since we're talking about why metal bearings fail, there's another type of metal bearing that's still used out there, even though it's a very, very old technology, and it's called Babbitt. They're produced using either tin or lead. The tin version is 90% tin, a little copper, a little antimony, and the lead is 75%, and the balance is tin and antimony. So all three of these materials are now regulated, which makes Babbitt kind of an interesting situation. I know there's some changes in the technology, but you know, antimony or antimony, depends on who you hear it said, but it is a carcinogenic, and of course tin and lead are both controlled through all types of ROS and WE and all kinds of other regulatory bases now. So, but Babbitt is still a very common practice, especially in certain industries. The steel mills still use a lot of Babbitt in their equipment. The hydro industry still uses a lot of Babbitt in their equipment. And like I said, it's been around for a long, long time, and it was really some of the earliest bearings used in the automotive industry for engines. And to this day, there's still a lot of hybrid bearing materials that use a combination of bronze and Babbitt. Power plants, electric motors. I mean, there's still, like I said, there's a lot of places. The big disadvantages of Babbitt's is fairly low load capacities. They have to be lubricated. Max operating temperature is 300 degrees Fahrenheit. Sometimes you get some bonding failures between the different metals. The biggest problem, I think, anymore is that it's a very expensive process, and there's very few companies left in North America that are doing this type of work. But like I said, there's still a lot of industries that believe in it and still use it. And they do require pressurized lube systems, like I mentioned before. So while they have their place, there's a number of places where Babbitt bearings can easily be replaced with self-lubricating composites, especially. If we look at the failures of Babbitt bearings, pretty common here: fatigue, bond strength problems between the Babbitt and the base metal, electrostatic charging, oil coking, varnishing, and wire wooling. And we'll look at each one of these individually so you kind of get an idea of what they are. But you can see in the picture here some of the sizes, and I think that's probably why Babbitt is still used a lot, because you try and use some of these large turbine bearings and use a rolling element, it's impossible, not only from a cost standpoint, but from a delivery standpoint. So, you know, I think Babbitt will always be here, but there are other ways to go. So if you look at fatigue failures, you know, this is a good example. This basically is just a loading situation where you can actually cause the lubrication to hydraulic out, and you get these dry spots. And this happens on a frequent and more consistent basis as it continues to move. And again, it all has to do with how much lube film is being generated. But you know, the lube, and often sometimes this happens in low pressure applications at low speed, because what happens is the film is actually wiped away from certain spots. You never get a 360-degree contact between a plain bearing, which Babbitt bearings are considered to be plain bearings. You don't get that 360-degree contact. So you're always going to have that issue of lube movement and dry spots, and movement and dry spots. And that in Babbitt leads to one of their key failures, which is fatigue. Bond line failure between the Babbitt and the base metal. While this doesn't happen often, it does happen occasionally where the Babbitt actually does not properly bond, and over time with heat generation, that tinning process to get the metals to bond to each other begins to fail. And so it really depends on the application and how thick the Babbitt is and what's going on in the application as to whether or not this Babbitt holds up to the test of time. I haven't seen too often this type of failure with Babbitt. It's usually something a little bit more obvious over this, but it does happen to occur every now and then. So, electrostatic discharge. This is really more towards electric motors and things like that, where you can actually start to see these discharge marks. You can see them here in these pictures. And this comes from arcing that takes place. And again, this would be primarily in rotary equipment, electromechanical type equipment. And again, it doesn't look to be an absolutely horrible condition. But over time, it does begin to get through the Babbitt and cause issues of failure. Oil coking. This is another condition that takes place when you have a very high load in a localized spot, and it leads to a temperature spike in that area, and that temperature spike causes the oil to actually overheat and cause this coking or this discoloration. Some people will now switch over to the new high pressure oils, the EP oils, which can take much higher loads and kind of resist these problems. But oil coking is something that I won't say it's really common, but if the conditions are right, it can happen pretty frequently. Varnishing, very similar to coking, but this seems to take place more when there's high pressures and high temperatures involved. And it's not just a contact area, it's the entire bearing tends to get this, and it's more of a buildup of the oil, and it's almost like a carbonizing that takes place. And even in polymer bearings, there are certain conditions where you can see a carbonization that takes place. On the good side of that, there's certain materials that we have, especially the composites, where the load actually increases the amount of lubrication that comes to the surface. In a lot of cases, it almost looks like a varnish, especially graphite-filled materials. That graphite comes to the surface, it gets this nice sheen, and that's actually a good thing. But in the case of Babbitt bearings, it now becomes not only a source of potential failure, but the key thing is that varnishing and coking and some of these other things we've already looked at lead to higher friction. Higher friction means more heat means more failure. Wire wooling produces a lot of damage. This is something that happens a lot in rotary equipment. And it seems to be materials that have high chromium contents, 3 to 20%. And so it really is a situation where as the contamination gets in, it starts to build up heat. As the heat increases, chromium converts to chromium carbide and from the steel shaft, and the whole thing begins to turn into this catastrophic breakdown and scoring of the Babbitt. This can happen in water pumps. Water pumps can get cavitation and leads to vibration, and that leads to loss of the water film and ultimately can lead to this type of failure. All of these are very, very unique types of failures, and it's really the nature of Babbitt and the applications and environments that these products are used in. And I won't say that Babbitt's a bad material, because it's not. It's actually a pretty good material in the right applications. And it's certainly a good material in areas where you can't get or don't want to pay for the extraordinary cost of large rolling element bearings. So why do metal bearings fail? We've kind of just bounced off of some of the different reasons that they can fail. Obviously, lubrication is a big part of that. And TriStar solutions all revolve around self-lubrication. And so as you look at metal bearing failures in your own environment, you might want to consider talking to us about self-lubricating. Now, as I mentioned earlier, we can't fix all bearing problems. It always comes down to a situation with fitting. With plain bearings, we're talking about materials that are press fit with a clearance on the shaft. With metal bearings, you're press fitting the inner race on the shaft, you're press fitting the outer race in the housing. And so it's a little bit different fit condition. So we sometimes have to work with our customers to kind of re-engineer how the bearing is being installed and applied and held into place. So not impossible to do, but I just want you to be aware that we're not a cure-all necessarily. But if your key failure is lubrication, or you're misusing a rolling element in an oscillating or linear application, or you're concerned about corrosion, these are all areas that self-lubricating plain bearings can be very good solutions for you. So that's the presentation. Now it's not. One more thing here. These are some of the materials that we offer in terms of self-lubricating solutions. I would recommend that you take a look at some of the other video presentations we've done. We've done them on the Rulon, the CJ family, Ultracomp, and Tri-Steels, and we will be adding some individual high-performance polymers and also some engineering information that helps you understand how to better utilize self-lubricating polymers and composites for bearings. So stay tuned and look back in frequently to see what we have to offer, because we do have some pretty good options for you to consider. So, see, we got some questions here that came in. Let's see, we got Robert from Tulsa, Oklahoma. Your statement on the use of rolling bearings for oscillating applications is interesting. I'd never thought about the lubrication issue you described. You mentioned you have several options for these types of applications, and we have dozens of problems. Can you talk more to that point? Well, I think, Robert, we just kind of covered that. The key here is always going to be material selection, and that's true with any bearing. You want to select a metal bearing based on what your load conditions are. Is it thrust and axial? You need to go to an angular contact bearing. Ours is a little bit easier in terms of how we fit these things and what we look for. We're looking for things like loads and speeds and operating temperatures and environmental conditions, what the hardware situation is, because all of that really comes into play as we look at how to replace bearings that are currently rolling elements. But we do have a lot of different solutions, and it really comes down to looking at your individual applications and saying, yes, you can use this. You need to change your hardware this way to make it work. Yeah, again, we have a lot of different ways that we can go, and it's individualized, literally individualized to the application. So, but please feel free to get in touch with us. We're more than happy to work with you at an engineering level, especially, and see if we can come up with something for you. Thanks for the question. Jenny at Clearwater, Florida. We use roller thrust bearings in small but heavy swivels used for rotary tables. The failures seem to come from load conditions that are usually outside of our normal design. We have always wondered if there's a non-roller bearing option. So have you had experience in this area? We have, Jenny, and you're right that a lot of times when you design a rolling element bearing, you design with the basics understood. We have the same problem with non-rolling element bearings, in that you can design around what normal is, but I tell you, 9 times out of 10, non-normal is the rule of the day. So the best thing that we can say is, yes, we have had a number of applications that we replaced roller thrust bearings. Sewage treatment plants, large diameter thrust bearings on the agitator spindles, dental chairs, believe it or not. We were able to take from a rolling element thrust bearing. It was actually a roller thrust bearing, about 12-inch, 14-inch diameter, and we were able to replace it with a composite PTFE, kind of a dual thrust component in there. Works quite well. Good lubricity, good flow. Gantry systems, large overhead gantry systems. So yes, the answer is we do have some solutions, and I would invite you as well to contact us and let us see if we can help you figure out some answers to your design. One more here. Clarence from Roanoke, Virginia. We're using very large double roller angular contact bearings in an oscillating application on railway service equipment. Shame on you, Clarence. It's exposed to a lot of contamination, so your pictures were very familiar. It sounds like we may have been using the wrong bearing system for 20 years. Yes, Clarence, maybe you have. Yeah, this is another situation where we would invite you to contact us, and let's talk through it, because we do a lot of work with the railroad, both undercarriage and also right-of-way equipment. So we've got a good amount of experience, understand what types of things you run into in your environment, and so we can certainly come up with some ideas for you there. So that's all the time we have for today, but we appreciate you joining us, and look forward to having you visit us on another video. Thanks.